Hi, I'm Andy.
And I'm Ronan from the Rainstorms, team number 8644.
In this video, we'll be talking about our robot and some of the key design changes we made along the way.
Right off the bat, we figured out that getting 10 freight in the shared hub, as well as the bonus, was equal to getting 10 freight in the Alliance hub, plus it was much closer. So we decided that we needed to use lots of defense, as we knew the shared hub would be a contested space. Staying on the wall made it easier to drive, as we could make sure our extensions went a fixed distance, as we'd be in the same place every single time.
So obviously we still wanted to be able to do the Alliance hub very well. The only difference for the Alliance hub is we needed the diagonal lift to reach farther because it was obviously farther from the wall. And through this diagonal lift and the horizontal extension, we had fine XY control of where to drop, as well as our wheelbase. We also wanted to collect with both sides of the warehouse when we were doing a shared hub, so we added a collector on both sides of the robot. First robot design was actually a vertical lift on a turret with the same horizontal extension. This proved to be superior for the shared hub as we got 17 cycles in 90 seconds all the way back in November. But it was too unstable to use the vertical lift as the horizontal extension caused the turret to droop and it was just too unstable. From this first design, we learned all of the things that brought us to this next design. And this current robot is what we call Sprint 3.5. As we were closer to Worlds, we focused on eliminating any possible issue that we could see happen in a driving practice, because we knew that winning or losing could be decided from one single mistake.
We identified a 6-wheel drivetrain as the superior drivetrain, as it allows us to get better traction for pushing other robots. We tried a drop center wheel, but we couldn't turn with it. The thin walls on our wheels allow us to fit between the gap on the shared hub, and switching to the Go Builda 30A wheels gave us better traction and didn't affect our auto capability. Our 6-motor drivetrain allows us to push on the shared hub in order to score more blocks. All our wheels chained together make sure that we had more power than other robots. We could easily go over the barrier and never get stuck thanks to a metal bar that made it so we wouldn't be balanced. We covered everything to not get stuck on the raised triangles on the edges of the barriers.
So for our collector, we really modeled it after the Rover Ruckus collectors because obviously the game had the same elements and there were some teams that were very proficient in collecting. And so we tried to make it as small of a container as possible so it would get in as quickly as possible, and we also wanted to make sure that the RPM was very high. So this is an 1150 RPM motor geared down 1 to 1.5 for this collector. This is a polycarbonate cylinder going around a 3D printed custom mount, and so we did the 3D print because we found it was the easiest way to mount the noodles onto a rotating shaft. And then the cylinder polycarbonate tube is to help protect the 3D print against defense so that it can't break. We have flex in this chamber right here with the top, because when a ball comes in, it'll actually push this lever down and this top will then clench the ball against the bottom, because we found issues that when we went up, it would lift so fast that balls would actually fall out of our collector because it was such a small container. We also added wall falling rollers here so that we could just go straight into the wall and the robot would automatically drive straight. We even cut sections under the noodles to allow balls and cubes to fit in on either side just for more collection. And we have this funnel here which rides essentially along the wall, which is just bent 1/16 polycarbonate. And so this will funnel the cubes into the collector. And then this piece right here is to prevent the funnel from getting stuck in the gap in the walls. So this part will hit first and then guide it so that it doesn't get caught. So we can come in any angle. And this 45-degree bottom is just to shave off those precious milliseconds of a cube getting stuck here, and so that it'll easily come into the container. We also separated the servo lift and drop for both collectors because they were obviously on separate sides of the robot and it just made it harder to make them one system. So what we have is a IR sensor in the back here that detects when a freight comes into the container. And then we use these servos from Pro Modeler that lift up this in about a quarter second. And what it is a polycarbonate bar mounted on a servo block with this metal string essentially that comes up And then we have a physical stop here near where the up position is for transferring. And then we have this spring here, so if somebody hits it, basically the spring will keep the bar in the box from passing by each other, so that when we go down, it's all nice and smooth. We changed this design from Arkansas because we had lots of stress on our earlier design, which was a string with pulleys to lift this up. And that's actually what failed in Arkansas. And so we spent, say, like a week right after Arkansas State Championship redesigning this entire subsystem because we knew we couldn't bear another failure like that at Worlds.
We found that the transfer speed was really critical to our cycle time and thus had to be optimized by making every part of it autonomous. We have a limit switch here that reverses the direction of our noodles when it collects and then is able to deposit them into our dumper. We use these Lego trapdoors that are just on O-rings, which don't allow the block to go through to the other side. We use an IR sensor in the dumper to be able to detect when our block is in the dumper, which allows for us to automatically close our door, securing the freight. We also use ramps at every point to be able to move our freight without having to use a servo or a motor.
We also spent many iterations on this transfer mechanism. It's probably the thing that we changed the most over the course of the second design. And we really just slow-mode videos of the transfer over and over and over again to see any place where a cube or ball could get stuck or take a long period of time. For our lift and extension mechanism, we split it up into two, as I mentioned before. This diagonal lift is strung using 4 pulleys, 2 up and 2 down, and it's belted by a motor that's seen below. We needed a pull down string because the lift was so fast that when we came down, the motor would sometimes unspin the spools, and we actually found that when we didn't have a pull down string, it was slow enough that we could actually collect the freight and transfer it before the lift came down. And so we added the pull down string just to make sure that we could always control the lift and didn't have to rely on gravity. We also did an analysis to push the limit to get the fastest motor possible for our stringing mechanism. So we tested many different motors, many different pulley ratios and spool diameters to ensure that we had the fastest possible lift. And so what we have is another 1150 RPM motor belted essentially 1-to-1 in about inch diameter spools for the stringing. And one thing that we actually changed in the season was we used the 2018 World stringing mechanism at one point where the string came up and then went across and then went over and down. We found that this worked, but it wasn't the fastest possible stringing mechanism because we essentially had to pull twice as much string to go up as we do now. And so we just split from that and we went for 2 separate strings that were all powered by the same motor. So we chose the 400mm door slides from Izumi because when you mount them at the diagonal, they still fit in the 18. Even though they stuck out from the robot, we thought that being 2 stages would be more beneficial than 3 or 4 because we could extend them faster, and then also it allowed us to mount the horizontal drawer slides below, provide some protection. And then we used the Long Robotics inserts. We actually slightly modified so that our strings wouldn't fall off. And then we used the Rev V bearings for the string. So for our second lift mechanism, we had this horizontal extension, which was very unique and was what pretty much set us apart from a lot of teams. And so we chose drawer slides because they were the lowest possible friction mechanism. They were also lightweight and very stable. We chose rigidity over weight because we realized although weight is very important, we needed this mechanism to be as stable as possible for reliable scoring in autonomous and Teleop. And one thing that we did that was special is we actually cut these last stages on these slides all the way down to their end stop so that they wouldn't hit the hub, and then we left the end stop and so that the bearings and the drawer slides wouldn't fall off. We had to use servos for extending these because our drivetrain uses 6 motors, and these servos are, again, Pro Modeler servos. They're very fast, and so this extends in like 0.3 seconds, fully extended. And we chose to use a linkage because we really didn't have any space for strings and pulleys, like our diagonal lift. And then we have this linkage right here, which is mounted down here, and this is in the same plane so that the rotational move it converts it into linear move it because it's constrained by the drawer slides. What we did earlier in the season is these bars were aluminum, and that was actually very detrimental because it caused these servos to break many times. We didn't use these servos, but we used blue servos. And so those were breaking very often, and we realized we couldn't continue that. And so what we did is we developed these polycarbonate bars right here that add some flex when we extend and retract. They're essentially servo savers so that we don't break the servos, and we actually have used these same servos since we switched these over. A couple things we added were these funnels right here so that when this arm would come back in, and because of the floppiness of the linkage, it wouldn't get stuck. We actually calculated the amount of rotation on the servo to inches per extension so that we could easily figure out how much to extend in Autonomous and Teleop for scoring. We also added these magnets on this bar right here and here so that when we come back in, the magnets will engage and fully bring it in. Because in order to save the servos again, we only partially retracted, but because of all the flex in the arms, it would engage the magnets and those would stick so that when we came back in, it would be ready for the transfer. One more thing that we added is this extra swinging arm. Basically, we had a ramp mounted on this scoring mechanism, but we found that it was just way too slow for the amount of cycles we wanted to do in auto. And so this extra swinging arm is 2 blue servos that travel about 180 degrees with our polycarbonate dumper mounted on them. And so essentially, it gets the freight as close to the collector as possible. So then when we lift and extend, we can basically bring it out while we're lifting and extending. And so we had to make sure that these servos were as fast as our lift and extension. And we added 2 servos for redundancy, so in case one broke, we would still be able to score. And this is mounted on the very end of our extension to maximize the reach of the robot. You can see the reach is very far from where the wheelbase is. And so it also gave us a lot of variability with the angle of dropping, which helped in Teleop. So our dumper is fairly simple. The only complicated thing is there's an IR sensor here to detect when the freight comes in, as we talked about before. There's also some slippery tape for the path when dropping to be smooth. And then we have just a simple door that opens to drop the freight with a duct taped washer on it so that we could pick up our team shipping element, which has a magnet and duct tape on it. And then for dropping it, we just open the door on the stick for it to pry off. And we tried to make this as lightweight as possible so that we could save the weight with lifting and extending. And we also added even more funnels here because when we came out, we wanted to make sure that it wouldn't get stuck on the arm. We also added 2 funnels here so that when the dumper would come in, it would auto center into where the transfer is and so that it wouldn't get stuck. So with this scoring mechanism that extended out of our wheelbase, we obviously had to think about defense and people potentially trying to break our lifts. And so we added these 2 steel metal rods on both sides of the lift to try to prevent anyone from touching drawer slides. And then we also used 2 sets of drawer slides to increase the robustness so that it wouldn't just flop around. So one big thing was our team shipping element. It may look simple, it might just look like a solo cup, but we added some foam inside it and then a magnet on top and this plastic washer so that it wouldn't tip over very easily. And so we used 2 different vision algorithms for this. We have just regular easy open CV color detection for the yellow, and then we also used the Naruko marker to get the X position on the screen of the webcam so we could differentiate where it is for autonomous preload. And then we realized we had to use the pre-existing lift system because it was so complex and it had so much reach that we couldn't just develop another arm or something to grab it because we were also limited on motors and servos. And so as I talked about before, we have this on the lid of our dumper as it reached the farthest from the robot. And so where we come down and grab it using the magnet in the washer, and then we'd be able to lift it up and then go and deposit it using this system.
We used foam on the inside of our cup to make sure that both TSCs would attract to each other but wouldn't attract to each other too much. We only had to use 3 buttons in order to reach out, grab the TSC, lift it up, and then extend out and drop it on top of the Alliance hub. Fast X and Y control of the dumper made it easy to aim the TSC.
So our robot wouldn't be fully complete without our duck spinner. We did testing very early on in the season to see what wheel would be the best with this VEX 393 high-speed motor. And so we did 10 iterations and we found that the Go Build the 100mm Gecko wheel was the fastest at a constant speed. But we didn't really focus on this as much because we found that a lot of teams could spin ducks, and we also knew that we were very proficient at capping the Alliance hub. So we basically just had it when we needed it, but we didn't focus too much on it. Next is how we controlled the robot. The biggest thing that we did that was very simple, but we found that not a lot of teams did this, was our robot automatically turned into the wall by default. And so that means we would never get caught on the barriers, and so we'd always glide through the gap. And what we had was an LED indicator to tell the driver if the robot was automatically following the wall or in regular drive mode. And we just had a toggle button on the controller. And so when we were not in wall follow mode, for scoring, the lift would still come up to the preset position, but the extender actually wouldn't come out at all. So this means that we could drive straight up to the hub without worrying about knocking it over. When driver 2 dropped the freight, the lift would stay up until the driver 1 drove away from the hub, and then they would have to do a manual down. We had preset buttons and positions for all of the Alliance hub levels and shared hub positions, and so essentially we would only have to press 1 button to score every time. So the lift and arm would all come out to the same position every time, and then the driver would just press 1 button again to drop it, and then it would all retract in automatically. We also had fine control of this extension back and forth by pressing down on our left or right stick on the joysticks. And so this allowed us to get fine placement of the freight on the shared hub and the Alliance hub when packing in a lot. We also had to figure out what to divide our controls for driver 1 and driver 2. Historically, our driver 1 has mainly done the driving of the physical robot and collecting, and that's what we did this year. So driver 1 basically drive into the pile, collect, and then as soon as this collects, it would automatically initiate the transfer and do that all by itself. And then once the freight came in here, we found that we could have driver 1 or driver 2 press the extend out button. We had it to driver 1 to do single person practice just for testing the robot. And then driver 1 would actually drop the freight because we found that on the shared hub you had to be very careful with positioning of your robot back and forth to avoid penalties. So we had the driver 1 do a lot more of the action.
We had 3 different driver 2s to make sure that we had as many people driving that wanted to as we could. And we made the robot as easy to drive as possible by automating a lot of tasks. And we had a spreadsheet of every single practice match with key details and observations such as score or what happened in the match. Then we picked drivers based on their score averages and went by the methodology that numbers don't lie. And if they wanted to drive, they had to be within 10% of the best driving pair in order to be chosen to run an actual match.
With our auto cycle time being very fast, we put a lot of automation into our Teleop to ensure fast cycle times. So as I mentioned before, we had literally 1 button to collect and fully transfer and auto extend to this point in our cycle. And when a freight comes into the dumper, it vibrates driver 2's controller, letting them know that it's ready to score, so that when they finally press the button, it'll then just have a short distance to angle out and extend. One thing we also added, when this lift was up and extended and the robot tilted just greater than 10 degrees this way or this way, it would automatically retract the whole lift system to protect it so that we couldn't break it. And at one point we had what we call the magic button. And so after the transfer happened, our driver 1 could press 1 button, have the robot automatically drive to the hub, drop the freight and then bring the lift back in. We didn't actually use this in competition. We played around with it a lot in driver practice, but our position tracking just wasn't consistent enough. So obviously a huge part of our autonomous was our position tracking wheel. It's the same wheel that we used last year in Ultimate Goal, and we switched to the Rev through-bore encoder because it gave us more control. It's actually linearly sprung for the first time ever in Brainstormer's history, so that we could go over the barrier without worrying about this getting hurt. And so it's basically just a 3D print with some oval holes for the screws, and then we have O-rings to pull it down so that it is always tracking on the field. We only did one wheel because of our 6-wheel drive. We could really only go forward and backwards. And then we also used the gyro for our angle when we needed to turn off the wall. Now onto the autonomous for this robot. This was our main focus after Arkansas, as it was not very reliable there, and we knew that we needed to have a very consistent auto to even have a chance to be a captain or even win Worlds. And so for autonomous, we actually had 3 collection positions in the warehouse. One of them was right along the wall, one of them was slightly into the pile, and one of them was very far into the pile. Because if you just went to the same position, you would keep pushing the freight away and you wouldn't have as quick collection times, and so you'd have slower cycle times overall. What we did is when we collected a piece of freight, we would grab that position and we'd leave it, then drive just past that position for the next freight, and so we could make sure to go as fast as possible for as long as possible without pushing the pile very far. And then another automation thing that we did was all of our transfer sequences was run in a thread outside of the regular drive sequences. So basically from the point that something's collected, we get the system time, and then we can track how long the whole transfer time's taking, and we then extend this out and lift up as soon as we get something in here. We actually did is we had this half extend towards the Alliance hub, and then we waited till we got closer because we found that when we were all the way angled out, it would hit the Alliance hub sometimes while it was still lifting up. And this is something we did just before Worlds because it was just another optimization thing that we noticed and we had to add. One other thing we did is we actually had time tracking of our entire autonomous broken down each part of the cycle, like collecting, transfer, driving to the hub, lifting, dropping the freight, and then driving back to the warehouse. We had comparisons between us and other top autonomouses in the world so we could see where we were lacking, what we needed to change in order to catch up. Some other things we did is we had auto exit cases on our autonomous to reduce the number of unneeded trips or unneeded extensions, and so if freight never got into the dumper for some reason, we would never lift up the scoring mechanism and we'd automatically just drive back into the warehouse to collect. In our code, we also had a state machine to track what part of the cycle the robot was in so that we could do more checks to determine when to do an action or when to go back for another cycle. And then also, we didn't have a fixed number of cycles for our autonomous. It was all time-based, and so after collecting, if there was less than 3.5 seconds, then it would know to stay in the warehouse and get those 6 points for parking.
Testing process is very unique as we run on an agile methodology, which starts with drawing ideas on a whiteboard and talking people through them. Then, we prototype a design for that subsystem and add motors and servos to test it, and then record the data that we can get from it in a spreadsheet. We put the best designs on our V1 robot in order to get it all moving, and then those best ideas moved on to CAD and manufacture to be a more clean system.
And then from there, we see what parts of the robot are holding us back the most in that cycle time. And we basically identify that problem and we decide to rebuild that subsystem or possibly the entire robot. And so we then go back through the full testing process to get a new design, and then we swap it into the robot and test it to see if it's better. And then if the limiting factor is decided to be the whole strategy of the robot, then we'll have a whole team meeting and discussion on whether we want to go back to square one. But it's really not square one because you know all of the knowledge from this failed strategy. And so you can make all those new decisions for your V2 design like we did here. And we try to keep all of those subsystems that were good to the next robot, and then we keep the ones that we didn't want to have intact just in case we need to fall back on that robot for the next competition. So rebuilding is something that our team isn't scared of. We know that we're not going to get the right design right off the bat from kickoff. So to make our whole design more consistent, we did tons and tons of driving practice. And we also ran our autonomous around 100 times between Arkansas states and worlds just to fine tune every possible issue because we knew the margins were so thin between us and the other top teams. We also did constant minor tweaks of our robot, whether it be small bent pieces of polycarbonate, slippery tape, little 3D prints to solve issues, and any issue that came up, whether it was driving practice or just testing or auto, we wrote it on the whiteboard as a to-do to fix. We put priorities on all of them, how often they happen, what we can do to fix them. We even went as far as to put electrical tape on our collector hubs because we had a ESD issue when practicing against our defense robot where it fried out one of our collector lift servos, and so we had to rewire our entire robot because we knew that ESD was a big issue and we wanted to make sure that we would always be able to play in any match. And then with more minor tweaks, we did tons and tons of slow-mo videos, time-lapse videos, or just regular videos on our subsystems to see really what's going on in every cycle and what can we do to make it better. For redundancy, we had a lot of systems with 2 servos. So up here, the duck spinners, the collectors, we have 2. Even the lift stringing, if one of them falls off, you can still lift up with one side. And so a lot of the design decisions that we made were about redundancy because once we got the scoring capability, we knew that we just needed a consistent robot to give us a good chance at Worlds. So for the wiring of this robot, we decided to put the 2 hubs right here below the lift because that was really the only spot that we had for them. But also it was nice to keep them low near the drivetrain so that we could keep all the wires protected. We put casing and ferrites on all of our wires because we were very scared about ESD after that defense robot incident. We rewired our entire robot 4 times by the time Worlds happens because you just can't run the chance of having a faulty wire in competition because it can cause major issues and be very hard to diagnose. Thanks for watching. Reach out to us by email, YouTube, Instagram, or Discord if you have any more questions about our robot. We'll be very willing to share.